By the end of 2025, 29% of all production code was entirely AI generated.
Which is just a wild number to actually say out loud.
Right. And, that number is currently expanding at a 45% year-over-year rate. Welcome to today's deep dive. When you really sit with that statistic and consider what it means for the industry, it just changes everything about how we look at software development.
Oh, absolutely.
The role of the developer is shifting right beneath our feet. I mean, we're moving away from drafting line-by-line syntax to orchestrating these massive complex systems.
Yeah, we are seeing a really profound pivot here. It's the difference between being a bricklayer and being a city planner.
That's a great way to put it.
Because, when you're planning a city, the infrastructure you choose at the very beginning, like the foundational pipes, the transit lines, that determines whether your city thrives or just collapses under its own weight as the population grows.
Yeah.
You can't easily rip out the plumbing once the skyscrapers are already built.
Yeah. Which is exactly why today's deep dive is so critical. We have consolidated a massive stack of industry reports for you today. We're looking at Strappy's State of React 2025-2026, deep dive comparisons of Go versus Rust, Prisma versus Drizzle ORM, Firecrawl's vector database benchmarks, JS Manifest's edge computing analysis, and IBM's breakdown of the model context protocol.
It is a lot of ground to cover.
It is, but our mission today is to cut through the noise of the internet and give you the definitive blueprint for the 2026 modern tech stack. We're looking at everything from the front-end user interface all the way down to the AI agent orchestration layer.
Because whether you are architecting a high-frequency trading platform or, say, a generative AI SaaS application, choosing the right stack today is the dividing line between effortless scaling and drowning in irreversible technical debt.
Yeah, totally.
The era of just picking a framework because it's trending on social media, well, that's over. You have to really understand the mechanics of what you are adopting.
So let's start right where the user actually interacts with your product, the front end. Looking at the data, there is a very real schism happening. React 19 has hit 48.4% daily usage.
Huge numbers.
It remains incredibly dominant. And despite all the noise over the last few years about pushing everything to the server, single-page applications, or SPAs, they still dominate the landscape at 84.5%.
Yeah, and the rapid adoption of React 19 is primarily being driven by the React compiler. For years, React developers dealt with this major headache, which was manual memoization.
Oh, right, the classic rendering traps.
Exactly. In the past, if you built a complex dashboard, every time a user typed a single letter into a search bar, the framework might try to redraw the entire page, like the sidebar, the graphs, literally everything.
Which obviously crushes performance.
Right. And to stop that, developers had to wrap their code in complicated hooks, like use memo, to manually tell the browser, hey, only redraw this specific chart if the underlying data actually changes.
And people always forgot to do it.
Always. But the new compiler analyzes your code and essentially does all that optimization automatically at build time.
Wow, so it just silently fixes one of the biggest performance bottlenecks without you changing how you write code.
Exactly.
But then, you look at React server components. The data shows they are the third most disliked feature, explicitly cited as a major pain point by 6% of developers.
Server components demand a completely different mental model. Suddenly, you have strict boundaries between what runs on the server and what runs on the user's browser.
Right.
And the biggest hurdle developers are hitting is contextual incompatibility. Imagine trying to pass a user's login state from the secure server side down to, like, a simple like button on the client side.
Sounds like a nightmare.
It is. Passing that data across the boundary breaks traditional front-end patterns, like the React Context API. It creates this highly fragmented architecture that is notoriously difficult to debug.
Yeah, I see developers pulling their hair out over this online constantly. With contextual incompatibility being such a huge hurdle in the Nextjs ecosystem, I have to ask, are we just forcing server-side rendering where it doesn't belong simply for the sake of framework hype? Like, if I'm building a dashboard where the user needs instantly reactive charts, bouncing back to a server feels like going backward.
That tension right there is exactly what is driving the current rebellion in the front-end space. I mean, Nextjs pushes a server-first architecture, which is undeniably brilliant for SEO-critical, content-heavy sites like e-commerce storefronts or blogs.
Sure, that makes sense.
But for highly interactive SaaS applications behind a login screen, forcing those server round trips can severely degrade the user experience. That is why the TanStack ecosystem, TanStack Query, Router, Start, is just surging as a cohesive alternative.
Good app everywhere right now.
It really is. It leans heavily into the client-first SPA model, but modernizes it with rigorous type safety and better data fetching. It gives developers the snappy interactivity they want without the server boundary headaches.
What fascinates me about this divide, though, is that the front-end ecosystem isn't just evolving based on human preferences anymore. It is being actively shaped by AI code generation.
Oh, absolutely.
Think about tools like V0 or Cursor. They are trained on millions of repositories, heavily featuring React and the SHAD Setia UI library. So when you prompt them to build a login screen, they generate more React and more SHADSyn.
Right, which then gets published.
Exactly. And that feeds the next generation of AI models. It acts like a massive echo chamber, cementing React's dominance as a self-fulfilling prophecy.
Yeah, AI tools will always reinforce the existing standard because that is where the training data density is highest. It creates a structural advantage for React that goes far beyond technical merit.
Oh.
But what keeps this entire ecosystem stable, actually, is governance.
Oh, right, the foundation shift.
Yeah, the React Foundation recently moved under the Linux Foundation. That move provides a neutral governance model, ensuring that React's core technical direction isn't solely dictated by a single corporate framework vendor pushing a specific server-first agenda.
So, if we are leaning into these highly interactive client interfaces, we have to talk about how we manage all the data moving around on the screen. The days of setting up massive, complex state management systems like Redux seem to be totally over.
Thank goodness.
Right. The shift is entirely toward the lightweight revolution.
Redux forced you to write an enormous amount of boilerplate code just to update a simple variable, and it wrapped your entire application in a giant monolithic store. The modern philosophy is to do more with significantly less.
Like Zustand. Right.
Yes, developers are flocking to tools like Zustand, which has a tiny, I think a 1.2 kilobyte footprint. It allows you to create separate independent data stores anywhere in your app without wrapping everything in complex providers.
That's so much cleaner.
It is. Or they use Jotai, which takes an atomic approach. It breaks state down into the smallest possible independent pieces that components can subscribe to individually.
And then there is prex signals, which introduces a fundamentally different mechanism. It actually bypasses the virtual DOM entirely.
Which is huge.
Yeah, normally React keeps a memory representation of your UI, the virtual DOM, and compares the old version to the new version to figure out what changed before updating the screen. That comparison takes computing cycles.
Right, it's expensive.
Exactly. Signals skip that process. If a user clicks a counter, a signal surgically reaches into the page and updates that specific text node directly. You save all those calculation cycles.
It's incredibly efficient.
But moving beyond just the user's browser, this lightweight philosophy is completely taking over the edge. And the undeniable star of the edge right now is Hono.
Hono radically redefines routing and edge deployment. If you look at older, ubiquitous frameworks like Express.js, they were built fundamentally on Node.js-specific APIs. They expect to be running on a traditional server that has access to a traditional file system.
But the edge doesn't work like that.
Exactly. Edge environments, meaning those globally distributed server networks like Cloudflare Workers, Dino, or Bun, they don't use Node.js APIs. They are built on pure web standards, like the native Fetch API.
So Hono basically ditches the Node baggage. I like to think of it like this. Express.js feels like a reliable old pickup truck that we've used for a decade.
That's a good analogy.
Right. It hauls whatever you need, but it's heavy, and it takes a second to get up to speed. Hono is like a Formula One car built specifically for the edge track. Because it relies strictly on web standards, it doesn't care if it's running on Cloudflare, Dino, or Bun. You write it once, and it runs natively everywhere.
And because it's so incredibly lean, you get sub-10 millisecond cold starts globally.
Wait, sub 10 milliseconds?
Yeah, guarantees that the moment a user requests a page, the routing logic executes almost instantly, regardless of where that user is in the world.
Okay, so Hono is incredibly fast for routing web traffic or doing basic authentication checks at the edge. But what happens when that traffic is asking your server to compress a 4K video or run an AI model locally or parse a massive data set? I mean, JavaScript is single-threaded. It processes one command at a time.
Yeah, that's where you hit the wall.
Right. The moment you give it a heavy mathematical task, it blocks all other traffic, and your latency just spikes. That's the ceiling of the edge. So to break through it, you have to drop down into compiled languages. And looking at the data, developers are heavily divided between two choices, Go and Rust.
Yeah, Go, or Golang, has firmly established itself as the pragmatic daily driver for cloud-native infrastructure, and Kubernetes microservices.
Mm.
It is really designed for concurrency.
Figoroutines, right?
Exactly. Bro uses lightweight threads called goroutines, allowing a server to handle thousands of simultaneous requests without breaking a sweat. And more importantly, it optimizes for developer velocity. You can take a developer who only knows Python, and they can be writing production-ready Go code in 2 to 4 weeks.
That's super fast. But then you have Rust, which is the undisputed king of high-performance AI infrastructure and WebAssembly. The trade-off, though, is the learning curve, which is notoriously brutal. You are looking at 3 to 5 months to become productive because you have to learn to appease the borrow checker.
The borrow checker. It acts as a hyper-strict referee living inside the Rust compiler.
A very angry referee.
Very angry. In most languages, if 2 different parts of your program try to modify the exact same piece of memory at the exact same time, you get a data race, which causes unpredictable crashes. Or, you forget to free up memory and your server slowly chokes to death.
We've all been there.
Right. But the borrow checker refuses to let your code compile, if those scenarios are even mathematically possible. It forces you to write perfect memory management up front.
So it literally just stops you from compiling.
It just halts. But the reward is that once your code finally compiles, it is fundamentally guaranteed to have no data races and no memory leaks.
And crucially, it doesn't use a garbage collector. In Go or JavaScript, the system occasionally has to pause your application for a fraction of a second to sweep up unused memory. Rust doesn't need to do that, so you get incredibly predictable performance.
Yeah.
And the market is responding to that certainty. I mean, the salary data from the Rustify report shows Rust seniors in the U.S. commanding $185,000 to $230,000. That is a $20,000 to $30,000 premium over Go developers.
It's a massive jump.
But I have to ask, is a $30,000 salary premium just hazard pay for having to fight that borrow checker for months? Let's be real. If I'm building a standard CR root app, just creating and reading user profiles, do I actually need Rust's zero-cost abstractions, or is Go completely fine for most of us?
For standard APIs that spend 95% of their time just waiting on a database to return a query, the performance gap between Rust and Go is completely invisible to the user. Go is absolutely the better, more pragmatic choice for those scenarios.
Okay, that makes me feel better.
Yeah, Rust complexity and the premium salaries that come with it are strictly necessary for specific domains. Think about inference servers processing massive AI models, or high-frequency trading pipelines.
Like the Discord example.
Yes. Discord famously rewrote their message indexing service from Go to Rust because those tiny garbage collection pauses in Go were causing latency spikes across millions of real-time messages. Yeah. When unpredictable millisecond delays ruin a user experience or cost millions of dollars, well, that is when you pay the Rust premium.
So we have the engine sorted out. We're using Go for our fast microservices and Rust for our heavy latency-sensitive pipelines. But an engine needs fuel.
Always.
And in 2026, that fuel is data. Specifically, how we handle high-dimensional vector embeddings for AI. A couple years ago, the industry rushed to adopt dedicated vector databases like Pinecone or Qdrant. But the paradigm has completely shifted to what developers call vector as a feature.
Maintaining a dedicated vector database alongside your traditional database was just an architectural nightmare.
I can imagine.
You had your users and orders in PostgreSQL and their associated AI embeddings over in Qdrant. Keeping those two systems perfectly synchronized in real time was incredibly complex. The industry realized that PostgreSQL could just handle both. Extensions like pgvector and the heavily optimized pgvector scale are completely dominating right now.
The Firecrawl benchmarks on this are actually kind of hard to believe. pgvector scale is hitting 471 queries per second at 99% recall on a massive data set of 50 million vectors. That is not a marginal improvement. That is 11.4 times faster than Qdrant.
It's staggering. And it achieves that speed through advanced indexing mechanics, specifically techniques that compress the vectors and localize the data in memory so the database doesn't have to scan the entire massive table for every query.
Which saves so much time.
Exactly. You maintain all the traditional guarantees of a relational database for your standard data, and you store the vectors right alongside it. It radically simplifies the architecture.
It is really like realizing your everyday Swiss Army knife already has the exact specialized tool you were about to go buy separately. Like, why carry 2 databases when one does the job flawlessly?
Makes perfect sense.
But to query those vectors, you first have to get data into them. This is where scraping tools like Firecrawl come in. They bypass all the messy HTML navigation and JavaScript rendering of a website, extract the raw information, and return clean markdown. You'd chop that markdown into chunks, turn them into mathematical vectors, and drop them straight into Postgres to feed your retrieval-augmented generation pipelines.
Getting the data cleanly into Postgres is half the battle. The other half is how your backend code actually queries that data. And this is where we see a fascinating showdown in the ORM space, the object relational mapper layer, specifically between Drizzle and Prisma 7.
Yeah, I'm looking at Drizzle, and it is a completely lightweight TypeScript native challenger. There is zero code generation. It acts as a very thin wrapper over standard SQL, and the bundle size is a tiny 12.2 kilobytes.
It's incredibly lean.
But on the other hand, you have the heavyweight champion, Prisma 7. They recently overhauled their entire engine. They ripped out the heavy Rust binary that used to power it and replaced it with a WebAssembly engine.
That swap to WebAssembly is a masterclass in optimization.
Really? How so?
Well, instead of forcing your server to download a massive precompiled Rust engine customized for every single operating system, WebAssembly allows Prisma to ship a tiny universal binary that runs instantly within the JavaScript runtime.
Oh, wow.
Yeah, that is how they slashed their bundle size from 14 megabytes down to just 1.6 megabytes. But Prisma still maintains its defining feature, which is its own schema-first domain-specific language.
Looking at these two approaches, Drizzle's tiny footprint and SQL-like control are incredibly appealing. But my worry is scaling a team. Like if I have an enterprise team of 50 developers all working on the same app, Drizzle gives everyone a lot of freedom to write queries however they want. Doesn't Prisma's rigid visual schema actually save massive teams from themselves by preventing schema drift?
Absolutely. It really comes down to organizational topology. Prisma's schema.prisma file acts as a centralized single source of truth. Even a non-backend engineer or a product manager can read that visual schema and instantly understand the entire data model.
That's a huge advantage for communication.
It really is. It creates a shared mental map across a massive organization, drastically reducing the chances of two teams accidentally diverging in how they structure data. Drizzle, on the other hand, appeals heavily to solo developers or highly specialized teams building edge-native functions, where they demand exact, granular control over their SQL queries and need the absolute minimum bundle size to hit those sub-10 millisecond cold starts.
So let's pull all these threads together. We have our vectors beautifully organized and synced in Postgres. Our edge APIs are efficiently querying them using Drizzle or Prisma. We have Go or Rust microservices handling the heavy lifting. But here is the critical pivot of 2026.
Here we go.
How do autonomous AI agents, the ones writing 29% of our code, actually execute these APIs and access this data without us having to write custom integration code for every single prompt?
This is the missing link that finally standardizes the agentic era. The answer is the Model Context Protocol, or MCP, created by Anthropic in 2024. It is an open standard that entirely decouples AI models from external data sources and tools.
I think of MCP exactly like the USB-C port on your laptop. Before USB-C, your monitor, your external hard drive, and your phone charger all needed different proprietary shapes to plug in.
Yes, exactly.
And that is how AI used to work. If Claude needed to read a local GitHub repo, you wrote custom integration code. If it needed to pull a Jira ticket, you wrote a different custom integration. MCP standardizes the shape of the plug.
The architecture is wonderfully clean, too.
Yeah.
You have the host, which is the AI application itself, like Claude Desktop or your IDE. The client handles the internal routing. And finally, you have the MCP server. The server is what wraps your local files, your Slack channels, or your Postgres database.
And the universal language they use to talk through that USB-C port is JSON RPC 2.0. Whether it is using standard input-output for a secure local file read or server-sent events to stream data from a remote database, the AI model doesn't need to know how to authenticate with Salesforce or how to format a SQL query.
Right, doesn't care.
It simply sends a JSON RPC request to the MCP server saying, hey, execute this specific tool, and the server does the heavy lifting.
And the adoption speaks for itself. IBM reported over 97 million SDK downloads by March 2026.
97 million.
Yeah. We are seeing frameworks like LangGraph natively orchestrating these stateful multi-step workflows using MCP as the backbone.
But this poses a massive shift for us as developers. If AI agents are navigating our systems via MCP instead of human users clicking through visual interfaces on a screen, we have to start designing our backends specifically for AI clients rather than human users.
It completely shifts the paradigm of software engineering from building features to platform engineering. Your job is no longer just building his user interface. Your job is building secure, observable golden paths.
Golden paths. I like that.
Yeah, you are building stateless NCP servers with strict permissions, aggressive rate limiting, and deep telemetry. You do this so that an autonomous agent can safely traverse your infrastructure, retrieve the data it needs, and execute actions without the risk of hallucinating a destructive command that wipes out a production database.
Which would be catastrophic.
Exactly. You are engineering the environment itself for the AI to operate within securely.
So let's recap the journey we just took through the modern stack. We navigated the front-end schism, seeing how the React compiler and the TanStack ecosystem are battling it out, heavily influenced by the AI code generation echo chamber. We pushed our routing to the absolute edge with lightweight tools like Hono running purely on web standards.
Sub 10 millisecond cold starts.
Exactly. Then we dropped down into the heavy backend, recognizing that Go is the pragmatic engine for microservices, while Rust is the hyper-strict zero-latency engine for when performance is absolutely critical. We anchored all of our high-dimensional AI vectors directly in PostgreSQL using pgvector scale, querying them efficiently through Drizzle or Prisma.
The Swiss Army knife approach.
Right. And finally, we wired this entire architecture together, standardizing how AI communicates with it using the Model Context Protocol.
It is a stack built for deterministic safety and orchestration. It is a fundamental shift toward an architecture where developers build the secure tools and the agents dynamically execute the workflows.
Which leaves us with one final provocative thought to consider. If AI is already writing 29% of our code today, and we're now universally standardizing the exact protocols like MCP that AI uses to execute our databases and microservices, are we unintentionally building a future where the underlying programming languages themselves become entirely irrelevant?
That is the million-dollar question.
Right. Whether you chose Rust or Go or TypeScript for your backend today, will the tech stack of 2030 just be plain English instructions, parsed and executed by agentic workflows, talking seamlessly over MCP?
Well, if we are truly transitioning from drafting syntax to orchestrating systems, human language might just become the ultimate orchestration tool.
Something to mull over while you're writing your next line of code. Thank you for joining us on this deep dive into the 2026 tech stack. Keep exploring, keep questioning the defaults, and keep building. We'll catch you on the next one.